Hello, class, and this would be our fifth lecture on AC network theory, and I've looked at all of the individual components and how those individual components, both how their impedance manifests itself in the circuit, and also how that changes the relationship between voltage and current traveling through the system. It's not always like it was in DC with the current in phase with the voltage, because now we've got current that's not in phase with the voltage, right? So we've seen that with both inductors and capacitors. Before I go on, by the way, I want to mention that it seems like the coronavirus pandemic should be coming to an end, right? I think I was probably the first one that even brought up the term coronavirus. And now I want to be the first one to point out that it seems that the pharmaceutical drug Ativan, which has been around for 30 years, is a successful treatment to the coronavirus. And in fact, it may even be a successful treatment to the Ebola virus. So positive things coming out, and it looks like we're turning the corner. We're going to, cut the mortality rate for coronavirus down to approximately the same as the flu rate. And so that's the good news. Anyway, so the first thing that I want to do today is I want to look at a regular circuit. Now, you're probably saying, well, aren't there specific applications for this? Yes. And the answer is yes. And I'm going to show you filters, a variety of different bandpass filters, band stop filters, how those work, and everything else. But the first thing that we want to do is we want to just look at a regular circuit. And of course, we have looked at this in class, but I want to look at it in more detail, not only how a circuit would work all the way around the circuit, but also how the current and the phase difference between the current and the voltage manifest themselves as we start to work our way around that circuit. And so now I want to make just a simple, easy circuit. This circuit is not going to be in resonance, and you might not even know what that means right now, but you will in a little while. So it also seems like my pen is not a fine point pen anymore. It's starting to get thicker and thicker and thicker. But here's what I'm going to do. I'm going to run a resistor, right, in line with an inductor, in line with a capacitor, right? So we've got all three of those together. And, if nothing else, this is a great way for you to learn complex number theory. And so we've got those three right there. I'm going to make the resistor just 100 ohms, right? Relatively small resistance, but the resistance is going to play a part in figuring out how the voltage and the current change as we go around the circuit. For the inductor, I'm going to say that that is a 0.1 millihenry inductor. And then for the capacitor, I'm going to go with a 1 microfarad capacitor. So we've got all three of these, and then we can just say that this is a 10-volt peak power supply that's coming in there. And the first thing that we want to do is we want to look at what is the total, just like we looked at in DC, what was the total resistance in series going around that circuit. We've got three components in series now, and we have to find out what their impedance is going around this circuit. So I think that everybody can see that for the resistor, if I was looking at the impedance for the resistor, that would be 100 plus J0 ohms, right? And if I wanted to write that in the phasor form, because we may be multiplying and dividing over the course of this lecture, I would say that that would be 100 ohms at an angle of 0 degrees. Okay, I don't think that anybody should be surprised about me writing this in the A plus JB rectilinear complex number notation, or me writing it in phasor notation. Now let's look at the inductor. Now we know with the inductor that it's going to be 0 plus j omega L. So we really have to know what omega is, right? And I'm going to say that the frequency for this circuit is going to be 1000 hertz. So if the frequency is 1000 hertz, then omega equals 2 pi f, right? 2 pi f, and of course its units are radians per second. So if it's 2 pi f, that would be 6,283 radians per second, right? And we know it's omega L, and we know L is 0.1 millihenry. Or did I say 0.1 millihenry? I'm sorry, that's 0.1 Henry. 0.1 Henry, or 100 millihenries if we want to look at it that way. So if I've got 0.1 Henries, then I can say that Z sub L is going to be 0 plus J, and omega 6283 times 0.1 Henry gives me 628.3 ohms. So that's what our Z sub L would be, or the impedance of the inductor. And then if I wanted to write the impedance of the inductor in a phasor form, it would be 628.3 ohms at an angle of 90 degrees. I think everybody can see that because this is all imaginary, right? So if it's all imaginary, then it's going to be at 90 degrees on the complex plane rather than being at 0 degrees. And in fact, if we draw the complex plane here, we can see that if I have resistance, right, resistance with no reactance, the resistance is all going to be real. Whereas if I have impedance that only has reactance, then the angle that I'm going to have is going to be that 90-degree angle. In fact, now this would be for Z sub L, and this is, of course, Z sub R, purely resistive, and then we're going to have another one down here that's going to be for Z sub C, and of course that's going to be at minus 90 degrees or positive 270 degrees on the complex plane. Now let's look at that last one, Z sub C. Now we know that the general formula of Z sub C is 0 plus J minus 1 over omega C, right? I wrote that. I haven't wrote that for the other ones because they were such easy equations to remember. But let's write this one out. Minus 1 over omega C. So if I wanted to write the impedance for the capacitor, that would be, I mean, think about it. We've got 6283 times 1 microfarad, right? A microfarad is 10 to the negative 6. So you've got a microfarad here times that, 1 times 10 to the negative 6 times this. Wouldn't that make that 6.283 times 10 to the negative 3? That's right. So if I have 6.283 times 10 to the negative 3, and I take the reciprocal of that because, that was 1 over omega, that gives me 159.16. Now, 159.16, we could really call that 159.2, right? So let's say that it's 0 minus, now I'm taking that minus there that's on top of the minus 1 over omega C, and I'm putting it out in front, 1 minus J, 159.2 ohms, right? So that's what Z sub C is going to be. And those are our three components. Now, when when we're actually, oh, I forgot to write this in phasor form. That would be 159.2 ohms at an angle of minus 90 degrees, right? So we've got Z sub R, Z sub L, and Z sub C all put together here. And let's add them up. I mean, that's basically what we're doing. We're trying to find the equivalent impedance, just like for the DC work, we were trying to find the equivalent resistance, right? So we're just going to add these three up. And of course, when we're adding, we want to use the rectilinear complex number notation, right? So I've got 100 plus J0 plus 0 plus J628.3 plus 0 minus J159.2, right? And of course, those are all ohms. I'm just going to put some brackets around here so that we realize that those are all ohms. So 628.3 minus 159.2 gives me 469.1. So my equivalent impedance in that circuit is going to be 100 plus J 469.1 ohms, right? Now, how would I turn that into a phasor? Because we're going to have to use that. Let's not forget that V equals IZ, or I equals V over Z. You probably realized I've written that in every one of the videos that we've had so far. So there we go. So I've got, I want to find out I, of course, and we know what V is because we know that V being a 10 volt peak reference form. So let's look at that. So if I've got V as a 10 volt reference form, the way that I would write that is 10 plus J0 volts. Or I could say that V is equal to 10 volts. And of course, I'm always talking about the peak voltage, aren't I? At an angle of 0 degrees. So later on, we have to keep it in our mind that we're always talking about peak voltages and not RMS voltages, so that when we do the power equation later on, we're going to be using RMS voltages, not peak voltages. But up to that point, we can, as long as we keep track of everything, what we're using, we should be fine. So let's go back to this equivalent impedance now. We've got that equivalent impedance in the rectilinear complex number notation, A plus JB, right? But now we want to turn that into a phasor. And so to do that, we have to square the one, and then we have to add the other component squared, and then equal those, and then take the square root of that, and that gives me 479.6. And you can see that that would be about right, wouldn't it? Because the square of 469 is so much larger than the square of 100. So I've got 479 ohms, and what angle are they at? Well, remember how we figure out the angle. We take the inverse tangent, right? Because we've got something here, we've got 476, and then we've got like 100 up here, and so we're really looking at that phasor right there, right? And so we know what the magnitude is because we square both of those, add them together, and take the square root under Pythagoras' theorem. But then how do we find this angle here? And I think everybody can see that we just take x over r. That would be the tangent. So we want the inverse tangent of x over r. And why don't I write that here, even though I've talked about that before. So x over r, and that means I get to write this one more time. So the equivalency of the impedance is going to be 479.6 0.6 ohms at an angle of, let me just do this for a second, 469.1 divided by 100 equals whatever, and then I just want to take the inverse tangent, and no, that can't possibly be, oh, I think unless I'm in radians, no, it says, so, oh, no, that's, of course that's right. 100, 469. I sort of drew this backwards, shouldn't I? It should have been more like this, shouldn't it? 400 and 469. And of course, that then would be 77.9 degrees. Let me just double check that again. Yeah, I got 77.9 degrees. So that's what our impedance is. And of course, we want to jump right from that because we know what our voltage is in complex form, phasor form. So we can figure out what our current is going to be. Because our current is the voltage, 10 volts peak at an angle of 0 degrees, divided by the impedance, right? And the impedance is 479.6 ohms at 77.9 degrees. So we can quickly figure out what our current is going to be. 10 divided by 479.6 gives us 0.0208 amps. And what angle is it at? Well, 0 minus 77.9. That gives us a minus 77.9 degree angle. And that's what our current is going to be. Let's put some circles around the things that we are going to be looking at and using here. Right, there's our current. Now we could say that that's 0.021 amps, or we could say that that's 21 milliamps, something like that, or 20.85 milliamps is what you really want, because as an engineer, let's not forget, we use 4 significant digits, right? So we've got that, we've got our voltage, and we know what our voltage is. So we're going to have to use our voltage in both the, because what do we want to do? We want to find out the voltage at A, and we want to find out the voltage at B. And again, we're going to have to look at these. We know that the current, even though we know under AC that the current flows back and forth, we always declare a direction, and that direction is always where that first positive current is going to be flowing. And so if it is a positive current, it's going to be flowing out here. And of course, we know at the second half of the cycle, it goes negative and it'll be flowing the other way, but let's not worry about that. We can do our analysis, our circuit analysis, by looking at the forward flow of that current. All right, well, we know what the current is. We know that we've got a resistor here. We're assuming that that resistor has current flowing through it from the left to the right, and so there's going to be a voltage drop across that resistor, right? And we know what the current is. So what is that voltage drop across the R1 resistor going to be? And again, we just use the, it's Ohm's law. Let's go back to Ohm's law and remember that V equals IZ. So the voltage drop across that first resistor is going to be the current that I've got, which would be 0.021 amps at an angle of minus 77.9 degrees, right? Times the 100 ohms. So 100 ohms at 0 degrees, right? Because that's what its impedance is. So we can find that the voltage drop across that R1 resistor is going to be 100 times 0.02. Well, don't we know of 0.021 that makes that 1, 2? Let's move the decimal point, and that's going to be 2.1, right? Now, amps times ohms is going to give us volts, right? So 2.1 volts, but it's at an angle. We've got minus 77.9 and 0. Let's add those together, and I get minus 77.9 degrees. And that's what we've got. That's our voltage drop, remember. It's not our voltage. It's the voltage drop that we have. And now what we have to do is we have to turn this phasor form of the voltage drop back into its complex number notation form, the A plus JB form, so that we can use it as we subtract it from the 10 volts that we started off with, right? Everyone realizes right as this is coming out of it that it's 10 plus J0 volts. So let's find out what the voltage drop is anyway. And how do we do that? Well, the way we do it, I'm going to write this out because I want everybody to have this in their notes. It's 2.1 volts, right, times the cosine of minus 77.9 degrees, right, plus J times 2.1 volts times the sine of minus 77.9 degrees. Does everyone see why I did that and how I did that? And of course, I think everybody, in the class who's worked with two-dimensional vectors understands how I'm going from the rectilinear to the polar representation or the cylindrical representation. And of course, that's all I've got here. So, and we could all assume, let's say cosine of minus 77, that's going to be positive, isn't it? So if I have the cosine of minus 77, that's going to give me 0.209. Really, it's 0.210. 0.210. So 0.210 times 2.1 gives me 0.44. So the voltage drop across the R1 resistor is going to be 0.440. Of course, that's only the real drop, isn't it? We've also got the sign here, and the sign of minus 77.9 is going to be negative, isn't it? So if I have minus 77.9 and I take the sign of that, I get 0.9777 or 0.978. That's what I'm going to call it. Minus 0.978. And so when I multiply that by 2.1, I get minus, I'm going to put the J there as my placeholder, minus 2.05. So there's our voltage drop, right? And of course, that's volts. Now, how do I apply this? How do I apply my voltage drop? Well, I know that I started out at 10 volts plus J0, 10 plus J0 volts. So let's find out. What is the voltage at A? I don't know what fell, but anyway, we're going to have to let that go in the background. I forgot to turn my phone off. He will get tired and hang up. So that's what we got. The voltage at A is going to be 10 plus J0 volts. And then minus. Why do I say minus? Well, it's a voltage drop across that resistor, isn't it? So 10 plus J0 volts minus 0.440 and then minus J 2.05 volts. And you're probably saying, well, of course, that minus is going to extend through there, so that's going to really become a plus, and this first one is going to be a minus. So 10 minus 0.44 is 9.56, so 9.56 volts. And then I've got to plus that, don't I? Because a minus and a minus gives me a plus, so that's going to be plus J 2.05. And that's going to be my voltage then at A. And you're probably thinking to yourself, well, how in the world could that happen, Scott? Or in your case, Professor Grenquist. How could that happen, Professor Grenquist? Because I started off with 10 volts, and now I can see that this, squaring this and adding them together and taking the square root is going to be greater than 10 volts. You're absolutely right. Thank you. Welcome to the world of AC network theory. That's right. It's not DC network theory. It doesn't work the same way. We use these concepts. I'm going to show you how we can use these concepts to trade current for voltage. I'm going to show you on the next lecture how we make the voltage maker. That's right. How do we actually make voltage? How do we get higher and higher voltages? Well, I'm going to show you, but not on this one. On this one, I want to sort of take us through so that we can see how the voltages work and everything and how they drop. So let's just look at this one, the voltage at A then. And how do I go back from the rectilinear thing to the other one? Well, of course, I just use Pythagoras' theorem, don't I? So I have 9.56 squared plus 2.05 squared equals, take it to the square root, and that gives me 9.77. Well, I guess it's not over 10. Oh, God. Did I? Yeah, I don't know. I guess, yeah, no, that's right. That's right, because it would be less than 10. All right. It didn't happen this time, but on the next one, it's going to go way higher. Just take my word for it. All right. So what's my angle then? And of course, my angle, like I said, and that's why I wanted to sort of take you through this all, is it's going to be the inverse tangent, isn't it? So it's going to be the inverse tangent of x over r. So if I have 2.05 divided by 9.56, that's x over r. And then I take the inverse tangent of that, I'm going to get an angle of 12.1 degrees. So that's what my voltage at A is. I mean, we can look at the voltage at A like this and say, okay, well, that's what it is in its rectilinear or complex number form. And then this is what it is in its phasor form, right? Does everyone see how that works? Now, we're going to go to another one. We're going to jump over this inductor now because we're going to have a voltage drop across the inductor. And we want to see what that voltage drop across the inductor is. And of course, to do that, the voltage drop, I'm actually going to write drop here across that inductor, is the current through the inductor times the impedance of the inductor, isn't it? That's going to be the voltage drop. Remember, we have to subtract that off the voltage that we got from A. So let's see how we've got this here. So I've got I, and we're multiplying two complex numbers together, so we want to use the phasor form of that rather than using the, well, we have to, using the phasor form of I, and the phasor form of I is 0.021 amps at an angle of minus 77.9 degrees, right? And then we've got to multiply that, and I guess I'm going to have to go down a little bit because I've got that extra z sub c there, but let's just put a dot there so that you know in your notes that I'm actually multiplying it by z sub l. And if we go back to z sub l, there is my phasor notation for z sub l, 628.3 ohms at an angle of 90 degrees. And again, remember, this is the voltage drop across the inductor. So let's multiply those two things together. 0.021 times 628.3, and that gives us 13.19. And 13.19 what? Well, okay, current times impedance gives me voltage, right? So 13.19 volts. And what's the angle that we're going to have? Well, I've got 90 degrees here. That's a positive. And then I've got minus 77.9 degrees there. So, 90 minus 77.9 gives me 12.1. I think everyone can see that that's going to be a positive. I'm actually going to write the positive there, although it's implied, 12.1 degrees. So that's our voltage drop, but of course, in that form, I can't use it, can I? I've got to get it in the A plus JB rectilinear form so that I can actually subtract it from the voltage that I have at A. Well, that's not a problem because I've got 13.19 times the cosine of 12.1 degrees. Let's do that first. 13.19 times the cosine of 12.1 degrees. And that gives me 12.9. 12.9. And that's going to be our real aspect. Of course, we also have to worry about, J. And I can see that J is also going to be positive, right? Because this is a positive 12.1. We're in the first quadrant, and that means that we're going to have a positive cosine and a positive sine. So I've got 12.9 plus J, and let's do the same thing. 13.19 times the sine, in this case, of 12.1. And that ends up giving me 2.76. So 2.76. And of course, what are we really talking about here? We're talking about voltage, and that's going to be our voltage drop. So what is my voltage at B? My voltage at B is going to be the voltage at A minus the voltage drop across the inductor. So the voltage at A minus the voltage drop across the inductor, right? So I've got 9.56 plus J 2.05 volts. That's what I had at A. And then I'm going to subtract off 12.9 volts plus J 2.76 volts, right? And I'm subtracting that off. Now, these are both positive, so they're both going to subtract. So 9.56 minus 12.9 is going to give me minus 3.34. Minus 3.34. And 2.05 plus 2.76 gives me 4.81. So plus J 4.81. And of course, those are in volts, and that's my voltage at B. If I wanted to look at my voltage at B in phasor form, I would square those two, wouldn't I? I've got minus 3.4 and 4.81. Where would that be in the complex plane? Well, it'd be minus is over here and then positive, so I would be in the second quadrant. The first quadrant is here, the second's here, the third quadrant is here, and then the fourth quadrant is there. And we see that in the complex plane, don't we? So I would have 3.34 squared plus 4.81 squared equals, taken to the square root, and that gives me 5.85. 5.85 volts. That's a 5. At an angle. And now you want to check this for sure, because what is this? Minus 3.4. You're going to be over here in the second quadrant, and then plus 4.8. So we know a couple things about that, don't we? If we're over here, minus 3, and then up here, we're probably someplace like right about here. So we know that our angle has to be greater than 90, but less than 180. Now, let's plug this in and just see how your calculator hates you. Because the inverse tangent, I'm going to just write this, the inverse tangent, right, of what? Now this is going to be 4.81 over minus 3.34, right? And how does your calculator know that the negative is in the denominator and not in the numerator? Because if the negative was in the numerator, then it would be down here, wouldn't it? Because if we looked at this number and the negative was here and the positive was here, then I'd be over here positive, I'd be negative, I'd be down in the fourth quadrant. So what is my calculator going to tell me? Is my calculator going to tell me that the angle is somewhere between 90 and 180? Or is it going to tell me that it's someplace between 270 and 0? Let's see, okay? So I've got 4.81 divided by minus 3.34, and that, and then if I take the inverse tangent of that, it gives me minus 55, which would be wrong and would kill everybody on that plane. All those poor orphan girls. Horrible, isn't it? And that's what we have to, you know, and that's why I've given you this example problem, to show you where it all falls apart once you get to your calculator and you don't understand the concept of complex numbers, right? This is a negative, this is a positive. There's no way your calculator can tell the difference between that. So you, as an engineer, have to understand which of the four quadrants it's in so that you can take this. In fact, I never put that negative in there really at all. Although you could say, well, this is minus 55 degrees. All I really have to do is add 180 degrees to that, right? And that then gives me an angle of 124.77. So this would be 5.85 volts at an angle of 124 well, let's just say 78 degrees. So that would be our voltage at B in phasor form. And of course, we have our voltage at B in rectilinear complex number form too. And I've got the A there. Now, the last thing that I wanted to do, and I'm probably taking way too much time to do this, is I just want to make sure that that's right for B. Because, you know, this being 0 here, 0 volts right there, I should be able to just add that impedance times the current going over C, and I should get the same voltage, right? I've come to this voltage by going from A down to B. Now I can come from this voltage here at 0 and adding the voltage in there. Let's see if that works. So I've got the voltage at C is going to be 0 volts, right? Because I start there, plus the current, and we know what the current is. It's 0.021 amps at minus 77.9 degrees. And then we want to add in the impedance of the capacitor, which is 159.2 ohms at minus 90 degrees. So when we multiply those two things together, I hope I've still got that all on there. Oh, yeah. So when we multiply those two things together, 0.021 times 159.2, we end up getting 3.34, right? 3.34. And oh my God, doesn't that look very familiar to that? So I've got 3 plus 3, 4. And then what's our angle going to be? Wait a second, B. 5.85 through. Well, wait a second. That should be 5.85, shouldn't it? Hey, just a second. Let me check this. I will get right back to you.